Hi everyone, this is Will. Happy New Year 2015. And to start off the year, I think it'd be fun to look at an implementation of miniKanren, in particular the microKanren implementation, which Jason Hemann and Dan Friedman at Indiana created to be sort of a minimal miniKanren. And since then, they've extended it, and I've worked with them on an extended version, and Matt might also. We've been working together to try to make it a little easier to understand. But I was thinking about looking at, let's say, classic microKanren, the first version, based on the Scheme Workshop paper that Jason and Dan had. So maybe we can look at that code, try to understand what's going on with the implementation, and hopefully. One of the goals would be, I think, that you could read through the paper and understand everything going on if you had any trouble reading it before. And secondly, we can just talk about any of the issues or questions that might come up with implementation. And I know a number of people have implemented microKanren and ported it in different languages other than Scheme and so forth. So if anyone wants to talk about or share their implementation, we can look at that and try to understand how it differs in Scheme versus microKanren. So I think that's the plan for today. And depending on how it goes or how much I fumble my description, maybe someone can bail me out who has played around with microKanren a lot. And also, we could hopefully get Dan and Jason on at some point, and maybe they can share their insights into it and what their motivations were for their design. So that's it. Today's going to be sort of a microKanren-y day. And I figure we'll have maybe one or two hangouts on implementation, and then we can start playing around a little more, maybe look at some papers and implement the papers in miniKanren, things like that. So I know there's some people interested in doing those sorts of things. To some extent, we are going to do that. We're going to take a paper and look at the paper and implement the code in the paper and talk about the code in the paper. So that is, I guess, our first example of looking at a paper and doing some implementation stuff. But of course, we're going to be implementing in Scheme, not in miniKanren. But at some point, we'll start implementing ideas from semantics or logic or whatever, programming ideas, graph search, whatever, in miniKanren. So, any questions before we start? Or? No. Okay, cool. As usual, if you have any questions, just type in a group chat. Okay, so I'm going to switch over to my Emacs buffer. And keeping with the live coding theme, I want to try to code up the system, and so let's call it muk.scm will be our mukKanren file. Okay. So this will be microKanren in Scheme. This will be based on Scheme Workshop paper. By Jason and Dan. And I'll include a link, but actually I'll just include a link right here in source code, I guess. So I guess there's sort of two interesting links to look at. One is Jason's GitHub repo that has the code. And the other thing is the link to the paper itself. And let's see, the paper. Okay. So this is the 2013 Scheme Workshop paper. Okay, so that's the paper and that's the code. So to some extent, this isn't real live coding, right? Because we're not. I mean, we're not really starting from scratch, right? I mean, we're more like we're going to just be entering code from the paper and talking about why the code is there and so forth. Okay. So I always like typing in the code just because I think it makes it a little. I think it forces you to pay attention a little more, just like writing notes. You know, when you write down notes, it forces you to pay attention more than if you just listen. So I always like to type things in, and also it can kind of focus our attention on the code as we're writing it. So what I'm going to do is I'm going to concentrate on the end of the paper. Actually, let me see if I can do this real quick. Let's try screen sharing the paper real quick. Okay, so here is the paper. And the last page of the paper contains an appendix. You'll also notice the mu sign here, the mu symbol. So one of the maybe unfortunate things about the naming is people weren't sure what that mu symbol meant. And it's supposed to be pronounced microKanren, just like we have miniKanren. So some people use the mu symbol in airports or when talking about microKanren. Some people wrote out MICRO for microKanren. Some people thought it was muKanren and they typed MU-Kanren. So if you look, if you want to search on Twitter, on the web, or something like that, for things about microKanren, you have to look for the Greek symbol, you have to look for MU-Kanren, you have to look for microKanren spelled out. So that's just beware of that. But the Greek symbol mu in this case is meant to be said as micro. Just like miniKanren is sort of a small version of the original Kanren system, microKanren is supposed to be a small core of the logic language, even smaller than miniKanren. Okay, but anyway, the core language of microKanren fits in this little one-column appendix, so it is very short. And this is the code that we're going to look at, and maybe a couple of variations, but it's very, very short, you can see. And you probably make it, well, I know you can make it even shorter. We could talk about that a little bit, but that's the code we're going to look at. Okay, so back to Emacs. Okay. All right. So when we're thinking about a miniKanren implementation, we should really think about how do we divide this up, sort of conceptually. What are the concepts in a miniKanren or a microKanren implementation? And there are a few concepts. One is we have some notion of logic variables. Okay. And that means we need also the ability, sort of going along with those, in addition to logic variables themselves, the ability to introduce logic variables, like fresh logic variables. And that's what the fresh construct gives us in miniKanren. We also need the ability to unify terms. Okay, so terms being lists, logic variables, numbers, whatever. So we need some way to unify things. And then on top of that, we have an operator equal equal, it lets us perform unification. And I guess we could also say somehow we have to have the ability to create terms. So we have logic variables, but we also, might have numbers, pairs, and so forth. Okay. So we have the ability to unify terms, ability to create terms. We have some notion of logic variables, some ability to introduce fresh logic variables, and associated with that, these are lexically scoped fresh logic variables, right? Okay. All right. And then, in addition to unifying terms and having lexically scoped fresh logic variables and all that, we also need some ability to have conjunction and disjunction. So we need to be able to have something like an and or an or in this case, like an and or, sort of logically. Okay. And we also need the some sort of interface operator with the host language, or this is like a query operator if you want to think of it that way. So this would be like our run, and this would be conjunction and disjunction. They're a little mixed up in full Kanren. Conjunction we get with fresh or kandi within the kandi clause, or within the body of a run for conjunction, and disjunction, that would be between kandi clauses. So conjunction is like and disjunction is like or, logically. That's how we can think about them. And then going along with the idea of the query operator, we need some ability to display answers nicely. And this is what we call reification. So we want to somehow take our representation of all these constraints we've built up and print them out in a way that, or display them to a human in a way that's readable. Okay. So let's see. I'm trying to think if there's anything else. Let me just look real quick. Yeah, so I think those are the main things we're going to be worrying about. So sort of underneath the hood, we'll see how we implement some of these things. Like it turns out that, to handle unification, handle conjunction, disjunction, we're going to have some plumbing underneath the hood. But these are sort of the things that we need to worry about in terms of implementing a logic programming system that looks something like miniKanren. Let's talk for a minute about sort of simplifying things. Let's talk about simplifying the language and the implementation. One thing that's really important to understand about the design of miniKanren is that miniKanren was designed to look a lot like Scheme. The syntax of miniKanren was designed to look like Scheme, and the reason is that Dan and I were teaching classes at Indiana on scheme programming, and miniKanren, we were using that to teach the students at Indiana about logic programming, and we were implementing in Scheme. Scheme was our host language, so it made sense, we thought, especially for the purposes of the book, to have a syntax that looked very schemely, so that you could play this game of translating Scheme code into miniKanren code, and if you saw a cond, then you could translate the cond into a condi, that sort of thing. So the reason condi looks like cond in Scheme is that we were just trying to syntactically resemble Scheme as much as possible. So that's a trade-off, because condi, if you have a condi that has a couple of clauses, let's say, and you have a couple of goals within each clause, or you could have, I don't know, you can have stuff like this, I guess. Let me do it this way. Okay, so syntactically, that's what a condi might look like. And if you think about what that condi really means, well, within each condi clause, there's really a conjunction. So this is like an and within each clause. So this is an and, this is an and, this is an and then between the clauses is like an or. Okay, so we're saying either, to get an answer, either this clause has to succeed, or this clause has to succeed, or this clause has to succeed. Any of them can succeed. Within each clause, all the goals have to succeed. So this is an or of.
How do you implement the fruit roll-up into the military tactics?
Wow. We haven't had a troll for a while. I always get worried when we don't have enough trolls. Oh, dear.
That was a serious question, though.
Yeah. Yeah. Was that Hunter? Help me out, guys. Who do I boot?
You're asking if it was me who's asked about the fruit roll-ups and the military tactics. That's me.
All right.
So.
All right. Okay. So anyway, I was hoping better trolling than that. We used to have like a weekly troll. He was actually pretty good. Okay. So we've got or and okay. So we've got a basically a disjunction of conjunctions. So is the way you can think of this, right?
So personally, I feel like if you have your fruit roll-up, then you're like more susceptible to being attacked. You see? But when you don't have it, people they're less likely to attack you because they're not as interested in you. You don't have anything that they want. And so it's kind of like you're more powerful with the fruit roll-up.
Huh. Interesting. Okay. Can you guys boot him, or do I have to like do it every time? All right. As long as you can mute him, that's probably fine. Yeah, it's just a wild new world. The dangers of having a public hangout. Okay. Anyway, so we have a disjunction of conjuncts.
It's muting me and kicking me out. That's not really cool. If you want me, like seriously, you're being rude right now. Just like listen to what I have to say or ask me.
All right. Well, I guess he can unmute himself, so that's going to be It's going to be a little annoying. Here we
Okay.
go.
Honestly, it's really not cool the way you guys are acting right now. I'm trying to state my point of view, and you keep.
All right, he's much more persistent than the previous trolls. Yeah, I know, I know. All right, what do you guys want to do? Keep going. All right. Okay, here we go. So, so we have a disjunction of conjunctions, right? Um, so what that means is we're sort of conflating the notion of and or here, right? So there's, um, Kandi has both an and an or, and then metaphorically, I mean, really what's going on, actually, depending on the implementation of miniKanren, this is actually exactly how it happens. You'll see that within each clause, within each Kandi clause, there really is a fresh nil. Because fresh is how we do conjunction. Like that. Okay, so fresh nil, you can think of that as an and. Okay, so that's an and. So a Kandi really is an or of a bunch of freshes. That's the way to think about it. So because of that, we really do have an or of a bunch of ands. So fresh, of course, itself conflates two things because fresh, in addition to acting like an and, also introduces new logic variables that are lexically scoped. So we could write it this way. And of course, these fresh logic variables x, y, and z will be in scope for these goal expressions, G1, G2, and G3. Okay, so fresh does two jobs. It introduces variables, logic variables, and it has, also behaves like an and of all these goals. Okay. So with the miniKanren, and fresh, also looks a lot like a lambda or a let in a lot of ways in Scheme. So once again, the syntax of fresh was chosen to be convenient for Scheme. But if we want to think just in terms of logic and not in terms of Scheme syntax or the convenience of having a syntax that's sort of higher level, then it's a little annoying that we're conflating these ideas of and or within Kandi, or introducing fresh logic variables and conjunction within fresh. So we might want to separate those out. So metaphorically, and the other thing I should say is that run is a lot like fresh. So if you do like a run 1Q, G1, G2, G3, then metaphorically what's happening is you're doing a run 1 and then there's a fresh Q. And then there's a G1, G2, G3. Okay. So the fresh is where we're getting the conjunction. So this part's like an and then the Q part is like a fresh. Okay. So run also is conflating two ideas: introduction of fresh variables with an and conjunction. So run, fresh, and Kandi all combine different ideas logically. If we look at the sort of the core ideas, we have and, or maybe it's probably better to call this conjunction, which is like an and. And then disjunction, which is like an or. And then the creation of fresh logic variables. And you might even think that the scoping of the logic variables is maybe a separate thing, depending on how you look at the world. And then, of course, there's like the interface operator and that interface query operator. And then there's something like, reifying the answers. And then we have unification. And we might want to draw a distinction between unification and equal, which is the higher level operator. Okay, so these are sort of the underlying notions that we have in something like miniKanren, and they just happen to be syntactically conflated because we have things like fresh, which combines creating fresh logic variables, introducing them in terms of scope, and having conjunction all at the same time.
So basically what my concern is I'm going to have the fruit roll up, and then all these armies are going to... I can't stand for that.
All right. So, can I delegate moderation? How do I do that? Let's see. The control center app. Control room. I see. Good. So, share controls. All right. Okay, here we go.
No, I'm working on enlisting.
Yeah, nice. Okay, sweet, cool. Now I get to concentrate on the coding. Thank you. All right, so we might want to have a very simplified version of the language just to try to make these ideas as clear as possible. Okay, and it may not be the simplest language to use, or our code may end up being very verbose. But if we're just trying to understand sort of the core fundamental ideas, then concentrating on these simple notions of conjunction, disjunction, and so forth, probably easier to understand than something like Kandi, especially from an implementation standpoint. And also, the other thing is, if we look at this Kandi, here we have a conjunction taking 3 goals. Here we have one taking 1 goal. Here we are taking 2 goals. Our Kandi itself is a disjunction of 3 clauses or whatever. So we might want to make some very serious restrictions to help make this language even simpler, or these notions even simpler. So we could do things like binary conjunction, binary disjunction. So we're going to take exactly two goal expressions, and we could say the creation of a single fresh logic variable and scoping of a single logic variable. So we can try to simplify the language as much as possible. And now, instead of that Kandi, we might end up writing that as something like this is a binary disjunction of a binary disjunction. Okay, and in the first binary disjunction, we have a conjunction of G1 to a conjunction of G2, G3. So now everything's binary, conjunction, disjunction. So this would be like our first clause up here. And then for the second clause, we have, actually we don't even need a conjunction because it's only a single case. So the G4 case. And in the third case, we have a conjunction of G5 to G6, like that. Okay. So this binary disjunction, binary conjunction would be equivalent to the Kandi. It's more verbose, maybe harder to read, but it's a simpler, it allows us to have a simpler notion of what's going on. Okay. All right. So that's what we're going to play with. A language that has these binary notions of conjunction and disjunction. Similarly, in terms of having something like a fresh that introduces variables, well, if we write something like fresh XYZ, and then goal G1, G2, G3, once again, this is combining a few ideas. So first of all, we could think of this as something like a fresh var of X, and then fresh var of Y, and then fresh var of Z. So we can introduce the variables one at a time, and then we could do a conjunction of G1 to a conjunction of G2 and G3. Okay, so we could break up the notion of fresh into introducing one logic variable at a time that's still scoped, and then having the body be conjunctions. And then we'll just say that the body of a fresh var can only take one goal expression, let's say. We can go even further than this, and we might want to. And the reason is fresh var, okay, so conjunction, like the conj and the dish that we're writing up here, we could write those as just functions that take two arguments. Okay, those could just be functions. But fresh var can't just be written as a function. And the reason it can't be just written as a function is that it's actually binding a variable. It's this is X is an identifier, a scheme identifier. So we would have to define fresh var and scheme as a macro using syntax rules or syntax case or whatever macro system or macro facility you want, which we could certainly do. One disadvantage of that is that if you wanted to port the system to a language that doesn't have macros, then it might be trickier. Okay, and we might want to tease apart the syntactic notions involving macros and variable binding and macros from sort of the underlying representation in a functional context. So another way to do this is instead of something like fresh var X and then say G1, what we can do is sort of break that into two parts. So we could do something like do let X be make var, something like that, to create a new logic variable. So that's one thing we can do. We have to be a little careful, though, with scoping. What we're going to end up doing is using the scoping mechanism of scheme to handle the scoping of these variables. Okay, and the easiest way to see it, and this is sort of underlying the let stuff, is to use lambda. So what we could do is we could have a lambda that takes some sort of new logic variable. This is going to take a fresh logic var, and then it's going to use the logic variable in the body. So, if we want to unify phi with that fresh logic variable, metaphorically, we can have something like this. And now, what we can do is we can call that function and pass it a new logic variable that we just created. Okay, so the idea is that we're going to use schemes lambda which has a notion of lexical scope, we're going to use lambda to handle the scoping of our logic variables. And we're going to create a new logic variable every time we have something like a fresh notionally. And then we'll pass that logic variable in to the procedure we get from the lambda expression. And the logic variable will be bound to the scheme lexical variable here. Like we could call this x. And the result of this would be similar to having fresh x equal x5. So this would be how we would write the equivalent of the fresh expression. We would break it up into the creation of a logic variable and then feeding in the logic variable to a lambda. And lambda is where we're going to get our lexical scope. We're going to get our lexical scope from schemes lambda using the host language. Okay, so that's another way that we can try to simplify things. We're going to rely on the host language's notion of lexical scope to give us lexical scope for our logic variables. Okay. One more thing, metaphorically, is that when we make the logic variable, we want to be able to make sure that we have the ability to express things like different logic variables, like x and y. Those could be different logic variables. So if we want to write something like that, well, first of all, we're going to need a conjunction. But we're also going to want to have some nested notion of this application. So this would be your y. And outside of this, we're going to be making another logic variable. And we're going to have a lambda x. We're going to have an application of those two. So this is how we can do something like introduce two different logic variables and use them in a computation. But we want to make sure that the logic variables we create really are different, and we can distinguish between them. So we want to know when we have an x versus a y and so forth. So one way we can do that, is to use some notion of equality, represent variables as like vectors or tagged lists or something like that, or cons pairs that we're consing up a new one every time, and then we could use scheme's notion of EQ question mark. So if we could say something like a variable is a vector of length 1. So if you're like make vector, x and make vector y or whatever is that kind of thing, then those two vectors won't be EQ. So this is like pointer equality. We're looking at the low-level memory addresses. But if we want to be a little more abstract, then what we could do is something like just have a counter that we feed through the system. And we'll have associated with each logic variable a number. And that number will allow us to distinguish between logic variables. Okay. So we have logic variables. We also have counter going around, that kind of thing. So if we get into, so at this point, this language is already like very close to microKanren in terms of how we're going to write things. That's the intuition, that's the idea behind microKanren. We're trying to break all of these ideas into very, very simple conceptual ideas as basically as primitive as we can get. Even if it means that something like fresh xy now turns into something more complicated, that's fine. We can add macros if we're in scheme on top of this low-level representation to give us back the syntactic sugar we want, but allows us to focus on sort of the simplest implementation concepts that we might care about. Okay, so we have conjunction, we have disjunction, we have the ability to create logic variables and distinguish those logic variables with a counter, and we're using scheme's lexical scope and lambda to give lexical scope to our logic variables. So that's part of the host language we're using. Okay, and then equal equal pretty much looks like the existing equal equal. That part doesn't change so much. All right. So metaphorically, that's what we're going to do. We're also going to get into we're going to have to look into some things like how do you implement equal equal, how does unification work, and so forth. Okay, so those are things we'll look at also. But that's a high-level overview of some of these notions. Does that does that make sense to people? Is that fairly clear? Yep. Okay, cool. All right, so let's go back in and dive in a little deeper. All right. What other ideas do we have implementation-wise? Well, or what can we avoid? If we go back to sort of the fundamental notions we have, binary conjunction and an or, we've already talked about those. Creation of a single fresh logic variable, scoping of a single fresh logic variable using lambda, or the hosts from the host language. Okay, we talked about that. Okay, so there's this notion of like a run operator, that kind of thing, and reifying answers. So reifying answers means that we have some underlying representation of all the constraints we've built up from calls to equal equal, but we probably want to clean those up to make it easier to read. But one thing we can do is just not really worry about that part so much, not worry about the interface so much. We can kind of defer this to a large extent. We can add these things once again with syntactic sugar, with macros and so forth, but we can just program in a very low-level style for now, just to try to make sure we have all the implementation pieces, and then wrap macros on top of the low-level stuff. Okay, so we can just defer that. We don't really have to worry about reifying answers, and to a large extent, we don't even necessarily have to worry about the interface operator. That leaves equal equal and unification. And like I told you already, equal equal, that already is a pretty simple operator. It just takes two terms, and so that one we don't really have to simplify anymore. We'll have to implement it, but notionally we don't have to come up with like a simplified version of equal equal. We'll have to figure out what unification is about. So we'll have to figure out how to implement equal equal and unification. So it's probably worth talking about those a little bit before we dive into the code, just to understand sort of what's going on. When we do something like unify 5 with x, okay, that's usually within the context of maybe some expressions, things like that. In fact, may already have done something like unified x with 6, and now we are trying to unify 5 with x. Okay. Well, it's important for us to have some mechanism for keeping track of all of the constraints that we've accumulated. Okay, so when we get into full miniKanren or constraint-Kanren, C-Kanren, or whatever, we have a number of different constraints. But right now, the only constraint we have is equal equal. And in this little snippet of miniKanren, there are only 2 calls to equal equal. So basically two calls to constraint operators. The first call, unifying x with 6, that's going to succeed because x is fresh, and we need to keep track of that information, though. We need to keep track of the fact that if we see an x again, like right here, that's the same as seeing a 6. The way we do that, the way we keep track of the constraint information, is with what's called a substitution. In general, we might have a notion of a constraint store, and the substitution might be part of the constraint store. So substitution is the part concerned with sort of unification constraints, like sort of the equal constraints. We could have a more general constraint store that includes the substitution and includes other things. Right now, we'll just think about the substitution because, like I said, we only have equal as our constraint. So, when we start out, we're going to start out with the empty substitution. And we might represent that, if we're representing substitutions as lists, that might be the empty list, let's say. Obviously, we could represent this many ways, with records, objects, if we're an object-oriented language, whatever, tag lists. But let's just keep it sort of short and schemely. We'll say we have the empty list for an empty substitution. After a successful unification, like unifying x with 6, we're going to extend the substitution. We're going to say that x is now associated with 6. So here's an extended substitution, which is we're using an association list. Okay, so we just have a list of associations. This is very simple, similar to an environment in our interpreters that we've been writing. Okay, this looks a lot like an environment. There is one important distinction between the substitution and the environment from our standpoint, which we'll get into in a minute. But right now, it looks a lot like an environment. Okay, so when we get to the second unification, we want to unify x with 5. What we're going to do is look up x in the substitution. And when we look up x in the substitution, we're going to see that x is actually 6. So this will be the equivalent to unifying 5 and 6, and that will fail. Okay. So the way we keep track of these unification constraints that we've been building up is through a substitution. And we're going to represent that substitution as an association list. The left-hand side of the association list is always going to be a logic variable, like x. Okay. Okay, so now why is the substitution, why is that a little different from an environment? Or when is it different from an environment? It's different because we can write things like this. If we started out in the empty environment and now we've associated x and y, now our substitution is going to look something like this. Or it might look like y to x. It doesn't really matter which one we choose. Okay, doesn't matter as long as we're always consistent with our code and handle things properly and don't make any assumptions that that we violate later. Okay, so this is different from an environment and an interpreter because we can have a variable mapping to a variable on the right. In the interpreter, we had a variable mapping always to a value. Or if you add a store, so you have a separate environment and a store, so you can map onto addresses and do set-bang a mutation, then the environment would map to addresses, and then the store would map from addresses to values. But in this case, we can have values, or sorry, we can have variables on the right-hand side. We could also write things like this, x, y, z. We could unify x with the list y, z. And in that case, we would have x to the list y, z. Okay, where these are like the variables y and z. Okay, so the substitution is different from an environment because you can have variables on the right-hand side, which you can't in an environment. So so these lists containing variables, variables themselves, numbers, whatever, those are things we're calling terms. Okay, so those are terms in the language. So substitution maps logic variables to terms. Okay, and yeah, so that's how we're going to keep track of the results of calls to equal is using the substitution structure. And we're going to use an association list. The nice thing about the association list is it's easy to extend, just like we extend the environment. We can extend the list by just consing on to the front of the list. So, you know, if our association list is this, you know, this sort of thing, that's our association list. And then within the context of that substitution, you know, we also unify, you know, W with 5. That's going to extend substitution to look like W5, and then we have this previous binding. Okay, we'll just build it up just like we build up a substitution. So that's all great. There is one sort of major complexity we get with this representation of a substitution. And there are multiple ways to represent substitution. The representation we're using is what's called a triangular substitution. Okay. And we'll see why that's triangular in a minute. The trickiness comes in, and it's not super tricky, but you just have to be a little careful how you handle it. The trickiness comes in when you do things like this. When you say, let's say unify x with y, and now we're going to unify, you know, well, actually, we're going to add some more unifications here in a second. But let's say we're starting out, right? Let's look at our substitution at each point in the program. So our substitution. So our substitution at the beginning. So we start with the empty substitution at this point, which is just the empty list. Okay, when we're so say this is our whole program really, right? This is like a run. So we start out with the empty substitution at this point. After this unification, which is successful, our new substitution is, instead of the empty list, is going to look like, say, x.y. It could be y.x. We just have to choose how we want our ordering to be. Well, let's say it's x.y. Okay, so that's our current substitution. Now we're going to unify, say we unify x with 6. Okay, x with 6. Well, one of the properties of our substitution representation and is that a logic variable appears on the left-hand side of a substitution at most once. Okay, so this is a property. This is an assumption we're making. Our code makes this assumption. We better not violate this assumption. Okay, so we're starting out with this substitution with x.y, and now we're extending, or sorry, now we're saying that x is actually 6. Okay, so this really means that x is 6 and y is 6. So we need to extend our substitution non-destructively because we're doing a non-destructive update. We are only extending the substitution by consing onto it. Okay, so we have to non-destructively extend the substitution so that now x will be 6 and y will be 6. So the way we do that is we're going to make sure now we have an association for y. So we're going to end up with y dot 6 x dot y. Okay. All right. So now, because x and y.
Can I ask a quick question?
Sure.
Is in the hall. Is it, did you extend with y equals 6? I would have thought it would be x equals 6.
You at this point?
So after you add the last equivalence clause in the fresh, where it's equals x6.
Yeah.
You're saying the consequence of that should be y dot 6. Am I following that? Okay.
I'm saying that we'll end up with this.
Okay.
Okay. Now, that's assuming that we decided. Okay, so it could have happened two ways. It depends on when we're unifying x and y, which variable we decide to put on the left. So we could have decided when we unify x and y, we take and those are both variables. We take the right-hand side, right, and put that on the left of the binding. In that case, we would have ended up with y dot x, and now we can extend it with x dot 6. And then it's simple. There's like no issue. We just do the natural thing and extend it with x dot 6. But if we started out with x on the left, if we sort of preserve the ordering in our cons pair, then we have this issue, because one of the properties we want to maintain is that each logic variable appears on the left-hand side of a binding only once, or at most once. Okay, so if we did x dot 6, then we would have x on the left twice in two cases. Okay, and it's not to say that we couldn't somehow handle that, but that would violate an invariant that we're assuming. And let me so. The reason that this would complicate things is that we want to be able to look up x just like we do normally in an environment. If we look up x just like it is in an association list, like using assoc or askew or whatever as a standard predicate lookup type thing, if we look up x, we'll see that x is bound to 6. If we look up y, if we look up the left-hand side, we won't see y ever bound. Y won't be bound to anything. So by making y be the left-hand side association, if we look up y, we'll get 6 immediately. If we look up x, notice x is bound to y. If we look up x, we'll find that x is bound to y, and y is a logic variable, fresh logic variable. And then what we'll do is we'll then look up y in the substitution. So we'll say that x walks to y walks to 6. So it'll be like a two-stage, it'll be an extra level of indirection. So if we we have this operator walk, let's say, if we were walking y in the substitution, then walk is basically just going to do like an askew. It's just going to do a lookup. It's just looking on the left-hand side of the pairs in the association list, and sure enough, it'll find that y is bound, and it'll just return what it's bound to. Okay. So looking up y works. We can also try looking up x. If we look up x, what will happen is we'll eventually get back 6, but it's through an extra stage of indirection. Basically, what will happen is x will walk to x dot y, and so we'll have a y on the right-hand side, and then y will walk to 6. So it's through an extra lookup. All right, so that's where we start getting sort of the triangular shape of things. Is that, if you were to try to visualize what happens when we look up x, and if instead of walk we have like a lookup, let's think of it in terms of a lookup. If we did a lookup of x or an ASCII of x to this, okay, then we're going to get back this pair, okay, and we would look at the right-hand side of that pair and see that that is itself a variable, and that would make us do a lookup of y in the same association list, and that would give us the y.6, and we would look at the right-hand side of that pair and say, hey, that's not a variable. Okay, if it's not a variable, then we just return whatever it's associated with. So at this point, that second lookup would tell us we had a non-variable value on the right, and we would just return it. So it's an extra level of indirection that we're doing in this walk. And it's sort of a triangular shape because well, let's see, what's the best way to think of the triangular shape? I guess it's a triangular shape in that we're going to have, in the worst case, the sort of n-squared behavior where we have to look deeper in the tree, or in the list. So, this is, in the worst case, an n-squared algorithm, because we might look up a variable that's the last thing in the list, and then when we look that up, look up the next last thing in the list. So, I could create a chain. I can create something that's pretty bad by looking up x in, let's say, x.y, where y is bound to z, and z is bound to w, and w is bound to v. If I did a walk of this, then I would have to look up x to get y, look up y to get z, look up z to get w, look up w to get v, and eventually this would give me back v as the answer. Okay, so v we would say would be the representative element of this chain of variables. So we have a variable chain. So basically we're saying x walks to y, which walks to z, which walks to w, which walks to v. So we look up x, and it'll eventually walk through multiple lookups. It'll eventually walk to the last element in the chain, which would be the first cons pair in this case, and that would be v. Okay. So we have multiple levels of indirection. It means our lookup is potentially quadratic. In practice, it doesn't seem that bad. It seems like, even though this is an n-squared algorithm, most of the time it works much faster. We could come up with other representations of our substitution that would avoid this problem. But other representations may have other issues. So the advantage of this representation of substitution is extending it non-destructively is super trivial. We just cons on a new pair. So that's a nice thing. But lookup is expensive. So extension is super cheap. Lookup is expensive. Lookup is potentially expensive. There are different tricks you can use to try to get the lookup lower, but you could also use totally different representations of substitutions, totally different approaches to substitutions, more sophisticated data structures. You could be using hash tables for your lookups, all sorts of things like that, all sorts of maps. You could be using all the closure, nice, the non-destructive data structures that Clojure has, that kind of thing. Would a hash map work? You would still have big O to the n possible worst cases for lookup of n variables. Yeah. So you could have a persistent hash table or hash map or something like that. I think Daniel's right. The issue is if you use this chain-based representation, if you still have triangular stuff, you might avoid the fact that you have to, the sin-squared behavior where it's a linear lookup, where the lookup can take as many steps as there is length of the association list. So the linear factor you would remove from the n squared, but you would still have potentially in a chain of length n. So if each lookup in the chain is still is big O of 1, constant time, you would still have multiple levels of indirection potentially. Okay, so it could be expensive.
Well, this is in the hall. I'm sorry. Can I interrupt? Can I ask a quick question about that linear chain?
Sure.
Do you know sort of like the find union?
Oh yeah, union find data structure.
Right, so if you walk through the chain and you kind of remember, well, at the end, okay, X actually points to V, and you sort of not only return that somehow as you're walking, you also allow yourself to mutate to kind of do what find union does to kind of, so you might have to have a order n cost once, but as you're kind of doing this, you're constantly pointing to the furthest link down. You're kind of rewriting all the links to point to V. For Y, for Z, for W, they're all going to point to V at the end. Do you know? I don't know if that would work, but that's kind of what happens where you get this sort of very slow growth and fine union where it starts out as n squared and they just kind of make it almost.
Well, one idea.
Constant.
One idea along that idea, or along one similar idea maybe, is to use path compression, right? Where I'm gonna mute you a second because I'm getting feedback. One similar idea is to use path compression, where when you would look up a variable, instead of that big long chain, you could allow duplicates and say, okay, well, we'll just say X. We'll extend this chain. We'll change the substitution now, or rebuild the substitution, or simplify the substitution, or whatever, so that maybe we'll add a new X. So now X will point directly to V, or let's say we eventually unify V with 5, let's say, right? That means every single one of these variables is now equal to 5. So if we know that it's 5, we could rewrite the substitution. So now everything is 5. So now W is 5, Z is 5, so forth, and the original X is 5. So that'd be another way we could do it, right? We could rebuild the whole substitution and basically do path compression on each element and find what each element walks to. Okay, so that's something we could do. We could do some path compression and keep around the old bindings and violate this property that we're not allowed to have duplicates. So we could do something like this, where even though X appears twice, because of the way we do a lookup, we're just going to find 5 right away. We could also do something fancier like union find, or we could have sets of elements that are together in a chain, right? We could represent sets that are in a chain. If we're going to make it destructive, then some of the other properties we have in miniKanren, I think, are going to go away, because so for example, there are very fast implementations of unification that use side effects, very fast implementations. But the whole idea of our implementation is we don't want to have any side effects we have to undo. In Prolog, they do side effects, and then they undo the side effects upon backtracking. They have this data structure called the trail that allows them to quickly undo side effects. What we're trying to do is not have any side effects in our implementation. I know Dan was very interested in union find at one point in time for unification. I think, and maybe we can talk to him about it at one point. I think he wasn't able to figure out how to do a non-destructive union find that was efficient. But I don't really know. That's not an area I've played around with. But certainly anything that would allow you to tell that something's in the same chain or same equivalence class, right? These are basically equivalence classes that we're creating. And we would just want to know, is this variable in the same equivalence class as another variable? That's often the problem we have. So something like union find actually would be really attractive. I think the problem was trying to come up with it in a persistent way that is fast. We've had trouble with, but that would be a really cool. Let me put it this way: if you could figure out a way to do that that's efficient, that'd be really awesome, and that might really speed things up. But yeah, so yes, that's a good idea. We've thought about the idea. We haven't figured out how to do it, but I don't think we've spent a tremendous amount of time on it. So if you can figure out like some persistent data structure way, sorts of things, closures like to think about that kind of thing, of doing like a union find type or equivalence class algorithm or something like that, that would be another way to do things, and it might have lots of nice properties that we don't currently have. Would a single level of indirection, like symbol goes to address, works well? Okay, so sort of like, are you asking like sort of like an environment and a store to give you an extra level of indirection, Daniel? Yeah, like an environment plus a store. Yeah, I think Dan and Jason have looked into this a little bit and have the store be an equivalence class. And I've played around with this a little bit a long time ago. The thing that I didn't have a long time ago when I was playing around with this is I didn't know about, well, I knew a little bit about, but I didn't spend time playing around with all these nice persistent data structures and so forth. But if you have persistent hash tables and multiple persistent hash, all these sorts of things, I think you could probably do much better. So yes, I think that's an area where there could be lots of experimentation. Another representation that I've seen was something Aziz Ghulam, who also did Vicari Scheme, which was forked to become, he did Icarus Scheme, which was forked to become Vicari Scheme. Aziz had an implementation of miniKanren that used binary trees, where what he did was he had a very clever algorithm to come up with these binary trees. Well, it's actually a trie, like a TRIE tree representation, where he gave a counter to each variable, just like I was showing before, but he would consider the counter as a binary number, and that number would tell you where in the tree the variable was. So he would do a trie data structure, persistent trie, and he would look up the variable by its number, and that allowed him to do like a logarithmic number of comparisons and go down the tree very fast. And that seemed to have pretty good behavior. We actually have there's a paper that Lindsay Cooper was working on, and Lindsay and Dave were working on this paper. I'll have to see if I can dig up a draft, see if she's okay with sharing with everyone, if Dave's okay with sharing it. But basically, we were working on a paper on really fast implementations of substitutions and lookup, and it was actually pretty cool. Dave Bender came up with this really nice benchmarking framework, and they were playing around with a whole bunch of different data structures, and some of the data structures, do much better than our simple association list, which isn't really surprising. But they were able to do quite well with some of these data structures, and they came up with pretty sophisticated, persistent data structures they were using. So there is a whole line of work in that. That paper never ended up being published, but there's a write-up of it and benchmarks and all that sort of thing. So if people are interested in that, I can ask them if they'd be willing to share. So Yeah, so these are all good questions, right? I mean, already, to a large extent, the substitution representation, the constraint store substitution, the constraint store representation, that drives a lot of your algorithms in miniKanren or any other logic system. Okay, and we're making specific trade-offs. The trade-off we're making is that extension of the substitution is completely trivial. Everything is immutable. So we actually don't have backtracking in our system at all. In a Prolog system, they have efficient backtracking because they can undo the side effects very quickly, the substitution, but they still have to do that work. We don't do any work at all. In some sense, we don't have backtracking. We just forget about the results. And everything's immutable. Everything's thread safe. We have all sorts of very nice properties because of that. But one of the trade-offs in our current model is that variable lookup is very slow, whereas it's constant time in Prolog. You have garbage collection. Well, we're able to rely on the scheme implementation's garbage collection. And yes, there's a ton of garbage collection that happens. So we do rely on that. In another sense, we don't have garbage collection, and I'll talk about that in a minute. Let's see. Daniel had a question. What proportion of time in miniKanren computation are walks? That's a very good question. The sense I get is it strongly depends on the program. Strongly depends on the program. And I think part of the problems we've had traditionally with miniKanren trying to optimize things is that we spent a lot of time doing things like optimizing the implementation to make the book run fast. Turns out the tests in the reason schemer are completely dominated by the arithmetic tests, in particular the exponentiation and logarithm tests, expo and logo. Those account for almost the entire running time. So in effect, when we were optimizing things, we were optimizing for expo and logo, and it turns out that many other programs in miniKanren don't have the same characteristics in terms of performance. So when we were optimizing expo and logo, we were sort of de-optimizing some other programs. So we've been trying to come up with a better set of benchmarks and benchmark tools and things like that. Things like the relational interpreter seem to behave very differently from expo and logo in some cases. So it depends. It's certainly very easy to create problems where you have really, really long chains of walks, and we're coming up with a more efficient substitution representation with the walks. Speeds things up tremendously. The bottom line is you spend a lot of time in walk because walk sort of dominates what happens in unification, and unification is the main constraint in the system. So a lot of time is spent in walk. If you can make walk much faster, you can definitely speed up the system. Even with this silly, naive association list representation, which we chose mainly just because it's easy to explain to people, there are all sorts of tricks you can use to speed up the walk. And I can talk about some of those. Some of those tricks and techniques are in my dissertation. For example, if you look at my dissertation, it talks about some of the techniques. Once again, some of those techniques will speed things up a lot, but they can potentially slow things down. So yeah, speeding up walk can be a big deal. It can really make programs much faster. Are these reason schemer tests online somewhere? Yes, the reason schemer tests are online. So let me grab real quick. I'll put in a link in the file. Go to my GitHub. Ah, okay, here we go. Let's go to the miniKanren GitHub. So if the code from the reason schemer, including the tests, is here. That implementation is a little old, so the other thing to look at that's probably better would be the simple miniKanren. This is like the cleaned up, more modern. simple miniKanren. So if you wanted to play around with the tests like in the book, I would look at this. As far as the benchmarks for, I need to put those online. The benchmark infrastructure we have is, it's a little wonky. It's not great. So, that would be easy, low-hanging fruit for anyone who likes doing things like benchmarking. Like I think part of the thing is, Dan and Jason and I, for example, we're all eager on trying to come up with new extensions to miniKanren or find better ways to explain it or whatever. We don't spend a lot of time doing things like creating benchmark frameworks and stuff like that, which would be very useful, but we haven't spent a lot of time doing that. So ideally, what you'd want to do, and what I've tried doing to some extent, is taking a bunch of examples, just a bunch of things like the arithmetic code or a theorem prover or whatever, and having benchmarks for that. Part of the problem is if you want to test just the simple miniKanren stuff, then some of the programs don't run. Like if you want to run, so for example, the relational interpreter, the Quine's generating interpreter, that involves some constraints other than equal. So you can't just take the simple version of miniKanren and run those programs without modifying them some. It might be worth modifying them some and saying, okay, even though the code isn't technically correct because we're allowing some terms that aren't really what we intend, from a benchmark standpoint is fine. So you could just remove some of those constraints and add a bunch of extra tests, so forth. But those are sort of the simple tests from the book, and you will see that if you come up with a better representation of substitutions, a more efficient walk or whatever, it'll definitely speed up the arithmetic stuff. Like it can cut those times in half or something like that. It's pretty significant. So that's a whole area, is trying to think of good algorithms for walking, good algorithms for unification, things like that, good representations of substitutions that are immutable. And I don't know that we have the best answer, and something especially like union find would be really cool. So that's really, those are really good questions. I will ask Dave and Lindsay if they mind if I put. Let me just check. I wonder if Lindsay or Dave have this paper up. Oh, okay. She does have this paper up. Here we go. Cool. Let me put a link to this paper. Yeah, so if you're interested in this topic at all, I would definitely recommend looking at this paper, and also maybe looking at my dissertation. I talk about a fair amount about how to do tricks with the association list to make things faster, but really having better data structures like this is much smarter. And I think the paper also briefly talks about the trie representation. So, and this paper was never published, I don't believe. So, and it's pretty cool. It has lots of implementation stuff, has lots of benchmarks. Dave really put together a really nice benchmarking suite, and yeah, actually, he's got this code for it. It looks like for everything. So the code. Let's see if I can. Is this code still up? All right, it looks like that code is no longer hosted. I'll see if I can find the updated location for the code. But Yeah, that's a great place for people to look, and a great place for people to experiment with is better representations of substitutions and walking and all that. David Nolan might be interested in benchmarking different types of programs. Yeah. Yeah, it's news to you that the recent schema version of miniKanren was optimized for Expo Lago. Well, the recent schema version of the code wasn't really optimized at all, right? I mean, it's very simple. What I mean is, if you look at my dissertation, okay, so there are some footnotes in the recent schema about ways you can speed up the walking. All of those little comments and ideas are based on our benchmarks for speeding up the tests, and the tests, like I said, were dominated completely by EXO and Lago. Yeah, so that was, I think, the danger, was that every time we were trying to benchmark things, we ran into trouble. And more recently with the microKanren stuff, we found similar problems that, whenever we would make a decision, an implementation decision, should it do it this way or this way? So for example, do the EQ test. Do we use an EQ test, or do we use a counter and numeric equality for comparing variables, stuff like that? It would turn out that the tests we use would sometimes make a big difference. And so you want a diversity of tests. You don't want one or two dominating. And also, you really want to be able to look at the tests individually, not just the total running time for loading a file, right? So our testing methodology wasn't very sophisticated, and I think we sometimes optimized for a couple of programs instead of like a wide variety of programs. And sometimes we de-optimized for other programs, we found out later. So yeah, that's something that definitely could do much better on is benchmarking, and also trying to figure out things like union find or more sophisticated uses of these persistent data structures. I think the try stuff that Aziz did was really cool. I'd like to. Anyway, so there's this nice paper that I've got the link to, and if you're interested in this topic, I recommend looking at that paper. It describes all this stuff. Okay, so yeah, so that's our representation of substitution, this triangular representation. So we could do another thing we could look at is path compression, right? Actually, let me. Yeah, so this. So this would basically be a path compression. Path compression would just, let us go ahead and make sure that when we knew the value of something, we just simplified the substitution to make it point directly to the value. There are lots of other ways you can represent substitutions as well, and and once you do path compression, you end up with what's called an idempotent substitution. So we have triangular substitutions. So triangular substitutions versus idempotent are two different ways to do it. So an idempotent substitution would be sort of like this path compressed version. What makes it idempotent is that if you have like an apply subst, if we had like an apply subst operator, right, and we had a term like x, y, and we're applying the substitution, this thing, to this term, well, with our triangular substitution, we're going to end up with a new term where x maps to y, y maps to z, so we're going to end up with this term. And then if we applied the substitution again to the new term, right, we're going to basically do a little bit of progress each time. But it's not idempotent. Idempotent just means that if we apply the same function more than once, we get the same answer back. So So now if we apply this term to y and z, well, y, let's see, y maps to z, so the first term is going to be z, first subterm is z, and z maps to w, so we're going to get that. And we'd have to keep applying this a bunch of times before we eventually got to 5, 5. Okay? So that's the triangular substitution. But imagine we did the same thing using the path compressed idempotent version. I mean, this is just the idempotent version, sort of rebuilt from scratch. In this case, we're going to immediately get back 5, 5, right? And then if we applied the substitution to 5, 5, we get back 5, 5 again, because there's nothing more to be done. Okay, so if we have this is the idempotent version, and this is our triangular. And the idempotent substitution is very mathy. That's what you read about when you read books about logic. They generally talk about these idempotent substitutions because they have nice mathematical properties. We've never been able to figure out how to do an efficient efficient representation of idempotent substitutions that was persistent. You know, we've used the triangular representation just because it's easy to extend. The problem with the idempotent substitution is after you do a unification, you might have to rebuild, you know, potentially the entire idempotent substitution each time. So if the substitution is 1,000,000 elements long, you have a lot of work to do potentially. Whereas with triangular substitutions, you have a lot of work for lookup, but you don't have a lot of work rebuilding. So if there's a way to do efficient, persistent, idempotent substitutions, that would even be better. We can get away with that, but I don't know how to do that, and we haven't looked at idempotent substitutions in miniKanren for a long time. Maybe something can be done with some of these tricky persistent data structures. I don't know, but idempotent substitutions would be much nicer, and it would simplify a lot of the code, I think. But we don't know how to make them fast, or building them fast after unification. And once again, that would be a good place for benchmarks, because building up the idempotent substitutions is expensive, but looking up an idempotent substitution, especially if you use like a persistent hash map, that would be constant time, right? So because we don't have a nice benchmarking framework and that kind of thing, making meaningful comparisons across a lot of test programs for different representations of substitutions and different types of lookup and stuff like that, that's not something we can easily do. So our current folklore thinking is that idempotent substitutions are too expensive to use, but we don't have any recent data for that. We would have to, so that would be an interesting topic to explore also. How are they really so slow? And if we use clever data structures, can you make it fast enough to be competitive? Even if it was just competitive, even if it wasn't better than the triangular substitutions in terms of performance, it would probably simplify a lot of the code. So that would be really nice. So that would be also something to explore, is playing around, going back to the idempotent substitution representation, seeing what you can do there. Okay, so yeah, we spent a lot of time talking about substitution representation, and that I think is appropriate because it turns out that's really at the heart of unification. This walk operator, when we walk a variable to see the value associated with the variable in the substitution, walk is really the linchpin of unification in our system, and it's also the linchpin of reification in our system to some extent. So walk, it turns out to be critical, absolutely critical to unification. So let's see. Well, let's do this because we're I don't think we're going to be able to finish the full implementation, but we've covered a lot of good stuff. Let's just look at how unification works, and let's end on unification, and then next week we can pick up on the other parts of how microKanren works, or and the stuff we're talking about in terms of triangular substitutions and walk and all that. That's pretty much true for any of the miniKanrens. It's not just microKanren. So if you look at the code and reason schema, you'll see the same sort of ideas. Okay. So just trying to explore the ideas and the data structures and stuff like that. And so now when you look at miniKanren, you should be able to understand at least what the ideas are behind everything. Okay, so we got walks and lookups and all that. We know what a triangular substitution is and all this. And if you want to play around with some of these other representations, feel free. So let's go ahead and just try implementing a definition of unify. Okay. So remember, we have walk already. We have a substitution representation. Remember, so it's going to be either like the empty list or an association list of like x dot some term, y dot some term, that sort of thing. Okay. All right. And so actually the first thing we should do is define walk. We should define walk first. What walk does is it takes a term and walks it in a substitution S. Okay. So for example, we could walk 5 in a substitution that is associating, x with 7 or 6 or something like that, whatever. And what that's going to do is it's going to return 5 because 5 isn't a variable. So in that case, it's just going to give us back the original term. If we walk a variable that isn't in the is not bound in the substitution, we will just get back the original variable like that. We could also walk a term that contains variables like x list xy, maybe in a substitution that has bindings for x and y. You might think that this is going to give you back 5, 6, but it's not. It's just going to give you back the original list. The reason is walk, unless walk takes just a variable on the left-hand side, basically it doesn't. It's like a no-op. Now we have something called walk star. That's a deep walk, and that's going to look inside the term. But for just walk itself, walk really only cares about variables on the left-hand side. So if we walk y in this substitution, that will give us 6. Okay, and yeah, so that's what walk does. Okay, so we're going to walk some term in a substitution, and there are different ways to write walk. I don't know. Let's come up with something. So let's one way you could do it. So we need some notion of var question mark. We need to know if something's a var. Okay. So what we haven't talked about is our variable representation. Okay. So we're going to have some variable interface, and that might be things like var. A call to var will make a var. Say we have var of some counter. Something like that, and we might have var question mark of some term, and and it will return true or false. Okay. And then we'll assume, we might also assume that we have like a var equal that takes 2 vars. This is pretty close to what you have in microKanren. Okay, so we have some variable interface. So we can tell if a term is a variable or not. If the term is not a variable, then we're just going to return the term itself. We don't have to do any work. Okay, so like when we're walking 5, there's no need to look down the substitution. We just return 5. If we're walking this pair or this list that contains variables, well, no need to look at the substitution because this, we're just going to return the term. It's only when we have a variable that we have to walk things. Okay. All right. So when we have a variable, then we can do some sort of lookup. We're going to look up the variable in the substitution on the left-hand side. One way we could do that, assuming we have the notion of equality, that we can use EQ or EQV or whatever on variables. Say we can use EQ question mark on variables, then we could just do something like AskQ, which walks down and looks them up. So that's the simplest version. This is what you'll see in the recent schemer, is the AskQ version. So we're going to take the variable t, look it up in the substitution, and that's going to give us some result. I don't know. I think we call it PR in the book. And if PR is true, then we're going to do this one thing, otherwise false. The way AskQ works in Scheme is if T doesn't occur on the left-hand side of an association in S, it's going to return hash F. Okay, so the else case means that we didn't find the variable that we looked up. If we didn't find it, then we just return the term. That's how we do this. So it'd be like the case up here where we looked up Y, we didn't find it in the list, AskQ returned hash F in the lookup, so we just return Y. Okay. If, however, AskQ found what we're looking for, like in this case, so we're looking up Y, and we have Y.6, what AskQ would return isn't the 6, it would return the pair Y.6. And that's a schemism because if Y were bound to hash F, you'd want to be able to distinguish hash F, the value associated with Y, from hash F. Y isn't bound at all in the association list. So that's why we get back a pair. So if we do have a pair, what we want to do is take the coder of the pair, that would be the right-hand side, the 6 in this case, and furthermore, we want to walk that. We want to recur. We want to walk the coder of the pair in the S. So the idea here is that if you walk Y, if you do an AskQ of Y and you say Y is bound to the pair Y.6, or you get the pair Y.6, then you want to take the 6 and do a walk again. The reason you need to do the walk again is because you might have one of these chains like we've seen before, right, where you have Y bound to Z and Z bound to 5. Okay, and you want that to give you a 5 in this case. So because in this case, if you do an AskQ on Y, it's going to give you back the pair Y.6 or Y.Z, so you need to do a lookup on the Z. Okay, and you need to keep doing that until you reach the end of the chain, where you will have, if you have the variable value at the end of the chain, you'll just, it won't be bound in the substitution at that point, and you'll just return it. Otherwise, if you have something like Z is bound to 5, then in the recursion, 5 will not be a variable, so you just return 5. So that's how walk works. You can define this various ways. Let's see how it's defined in the microKanren paper. All right, so here's the microKanren equivalent. Okay, so that code looks quite different, but it really is very similar. So one thing is different is it's using this define syntax where you have parens wrapped around the name of the function. So this is really the same thing. It's just syntactic sugar for define walk to be lambda us. Okay. I'll just go ahead and expand that. I guess they're trying to save a few lines of code. Okay, so that's what we got. And let's redefine u to be t to make it a little closer to what we have up top. Okay. All right, and let's make this if. Well, I guess we can keep that if right now. Okay, so let's see. Let pair be and a var of t. Okay, so they're doing the var t test, except they're doing an and instead of having a different con clause for it. That works also. If it's not a variable, then this and will be false, and then pr will be false, in which case you just return the original term. So actually, this is very similar to our cond up top. This would be similar to writing it this way. So you can see the else t here, Both of those happen if t is not a variable. So here's the var t, here's the var t. Similar sort of idea. This is just written in a shorter style because they're trying to save on characters, I think. You can see here the lookup, the ASCII lookup, is similar. They're still looking up in S, but instead of using ASCII, which is using pointer equality with EQ, they are using ASP, which is something in R6, R7, I would say R6 RS scheme. It's a version of lookup or association list lookup that takes a predicate, takes an arbitrary predicate instead of like ASCII for EQ, assoc for equal, question mark, semantics. You can give it a predicate that will stay when you found a left-hand side that's equivalent. So this lets us parameterize walk by our var equal question mark, right? So that's part of our variable interface. So this allows us to be a little more abstract. We don't have to assume that variables are EQ or have EQ semantics. So this would also be useful if we wanted to go to a language like Haskell, which doesn't have pointer equality. Okay, so, or if we wanted to work on records or whatever that might have a different notion of equality, this allows us to abstract over that. So we just have an abstract notion of variable equality, but it's the same sort of thing. We're just doing an association list lookup to get a pair, and here's their cond. If the pair is true, then they're going to walk on the coder in S. That's exactly the same thing here. Else T. So this code really is the same code. It just looks very different. I mean, it looks structurally different, but it's the same thing. The main thing is that this code makes an abstraction over variable equality. Okay, so that's the main difference. But that's how walk is implemented in microKanren or In various versions of miniKanren, you'll see slight variants of this, but that's the idea. Okay, so now we have walk, and we know what that does. And finally, we can now define unify. So let's just take the unify from microKanren. So you notice the first thing we do, we have these two terms, u and v, coming in. The first thing we do is we walk u and v in the current substitution. So unification, we're unifying two terms in the current substitution. So maybe x and y in some substitution that might make x, might associate x with 5 and y to 6, or associate them both with 5, or who knows what. But we're going to walk both of those terms in the current substitution to get sort of the end of the chain. Walk down those variable chains until we get whatever values at the end. It could be a fresh logic variable. It could be some arbitrary term bound to that chain. Or maybe the variable isn't in the substitution at all. Or the term may not be a variable at all. The term could be a list. The term could be number 5 or whatever, in which case walk just returns that value. Okay, so in any case, the point is if u or v, if either one is a logic variable, we're going to walk that in the substitution to get whatever is associated with that variable in the chain. Okay, so now we actually have the walked values of u and v, and we can do a con based on that. And there are going to be a few cases here. I'm going to use the square brackets just to make it a little easier to see, to parse visually. Okay. So one case is when the walked value of u is a variable and the walked value of v is a variable. When they're both variables, okay, well, what's going to happen when they're both variables? So that'd be like, okay, we had fresh x, y. We could unify x and y together, for example. That would be one case that could happen if they're both variables. The other thing that could happen is we're unifying x with x. If we're unifying x with x, then we don't really have anything to do. X is already equal to x. Okay, so that's sort of a no-op. So if the variable is the same, if u and v are the same variable, there's really nothing to be done. So we're going to have this extra test there. So if u and v are the same, just return the original substitution coming in. Unification is either going to return some notion of failure, or it's going to return a substitution. Okay, take substitution, returns either a substitution. It's like a maybe substitution, I guess, in Haskell or whatever. So that would be one case in which we just return the current substitution is when we're unifying x with x. The other thing that could happen is if we unify x with y, let's say that's already happened, and now we unify x with y again, well, let's look at the substitutions. Okay, so say the substitution originally started out empty. After unifying x and y, we're going to have something like x dot y as our substitution, right? When we then unify x and y again, or maybe y and x, doesn't really matter, just for fun. What's going to happen? Well, the first thing that happens is when this would result. Okay, what's going to happen? We're going to have a call to unify yx in the substitution where x and y are associated with each other, right? And because we're going to walk both x and y, the two terms coming in the current substitution, y and x are both going to walk to the same thing. They're both going to walk to y. So that's basically what will happen is when we do this variable comparison, yes, they'll both be variables, but they'll both be the same variable. They'll both be y. And in this case, we don't have any work to do. This really is equivalent to just unifying x with itself or unifying y with itself. So we would also hit this case because remember we're doing the walk steps first. We're walking y. Y is going to walk to y. X will walk to y also. Okay, so those two cases are both handled by this. So this case would be handled by this Kanren clause. Okay, not the first one though. So that's one of the cases we have. We have two variables and they're the same thing, or they walk to the same thing. Okay. Another case that could so when they're both variables. Okay. Another case we have is if u is a variable. Okay. So if we reach this case and u is a variable, that means when we walked u, we got to a variable. What else do we know? We know that since the first clause failed, we know that either v isn't a variable at all. It could be like 5 or a list containing stuff. Or v is a variable, but it's not the same variable as u. Okay, because if u and v walk to the same thing, then we would have hit the first case. So what we can do in this case is just say, look, u is a fresh variable. We really don't care what the other term is. We know it's not the same term, so we're going to have to extend the substitution. So let's just go ahead and extend it. So we're going to extend the substitution uvs. And this xdes, we can go ahead and define it. Xdes is not very interesting. Xdes basically is just a call to cons, or two calls to cons. Basically, we're just going to cons of uv onto s. That's all it is to extend the substitution. We're just consing onto it. We're associating u and v to the front of the association list. The other way we might write this is using back quotes and commas. This would be u dot v dot s. Okay, those are equivalent. All right. So basically what's happening is if we know one side is a variable and we know the other side isn't the same variable, we can just do a variable extension. That's it. If v is a variable, we can do a similar thing. We just have to swap the order. Now we're extending v is going to be on the left-hand side, u is on the right-hand side. Now in this case, we know that u is not a variable because otherwise we wouldn't have reached this case. So we would have hit this case. So here we know we're unifying a fresh variable u with a non-fresh variable, with something that's not a variable. So we're going to extend it the other way. Okay. So we have some asymmetry there, and we could, of course, we could swap those two terms if we want, or those two clauses if we want. So that handles the cases when we have a variable. If u or v, the walked u or v is a fresh variable. We also have a pair case. So we might have a pair. In fact, if u and v are both pairs, then what we're going to try to do is unify them pairwise, right? So maybe we have something like, 5 dot x, and we're trying to unify that with 5 dot y or something like that. Now we're going to do a pairwise unification. We're going to try to unify the cars, like so unify 5 with 5, that would succeed, and then unify the cooters, unify x with y. Okay, so we're going to do pairwise unifications on the cars and the cooters. So what we're going to do is we're going to recur. We're going to try unifying the car of u and the car of v, and that may or may not succeed. And when we're unifying it in the current substitution. Okay. So we're going to let bind some new substitution s to the result of the unification. Now this s isn't necessarily a substitution. This could be like a false value representing failure. Okay, so it's really like a maybe yes or something like that if you're in Haskell. So what we need to do is do a test. So one way to do it is like we could say like if s, then we're going to do some work. Otherwise, we're going to fail. Say we failed. And if it succeeds, then we're going to unify the coder of u and the coder of v in this new extended s, or new potentially extended s. Okay, that's the idea metaphorically. In microKanren, in order to save space, to be succinct, instead of writing it as an explicit if, they used an and, which logically ends up being the same thing in Scheme. Because in Scheme, Booleans, anything, you don't just have and on Booleans. Any value that's not hash f is considered true. So a substitution, even an empty substitution, is considered true. All right, so that's the pairwise unification for pairs. And then finally, we have an else case. And then here we're going to default to the host language's notion of equality on terms, on things like numbers and so forth. So maybe we're unifying two numbers, for example, right? We want 5 and 5 to unify, but 5 and 6 to not unify. We're going to use the underlying host language's notion of equivalence to determine if those two are the same. And in core logic, you'd probably use some protocol on equivalence or the different objects or things like that to try to make the unification more generic. I know core logic has an extensible generic unifier. And that's it. That's what unification does. It's basically a type of equality is going to return a substitution. If the unification succeeds, it will return a substitution that would make the two terms you're unifying equal, right? So if you're unifying 5 and x and y and 6 in the empty substitution coming in, then going out is going to be a substitution that's going to associate. Remember, this is a pairwise unification, so it's going to we're going to associate y with 5 and x with 6, or the order of these two could be different. x.6 could be before y.5 or whatever, but depending on exactly how you did the pair lines, like if you're doing the cards or the coders first, for example. But that's the basic idea of unification. It's actually a very simple definition once you have walk in place and once you know your substitution definition. Okay, so it's really the substitution and the walk that's the tricky part of unification. Unification itself is almost just like writing the equality predicate equal question mark. It's very similar to equal question mark. There's one other thing that we've left out. So here our xs, is always returning a new extended substitution. What we've left out is the equality, the occurs checked. So if you remember, in miniKanren, if you unify x with the list containing x, that will fail even if x is fresh. Okay, so you're not allowed to unify a variable with a term containing that variable. That's not allowed because this would produce this would produce an infinite term. If you're going to allow infinite rational trees in your language like Prolog 2 does, then that's fine. But if you're going to restrict yourself to finite trees as part of your term language, then unification is only sound or only correct if you disallow these sorts of self-reference. Okay, so we are not including the occur check right now in our unifier, which means that unification is equivalent to unifying x with the list containing x. Those would succeed. And if we naively tried to print out X, we would get back this infinitely nested tree that would never finish printing out. We'd have to do some cycle detection or something like that. But anyway, this is a basic version of Unify without the occur check, using triangular substitutions, and we're doing walks on the terms coming in. Every time we make a call to Unify, including recursively, we end up walking those variables. So you can see how much walking is happening. Walking is happening all the time. And if you have deeply nested data structures, as you push down on those data structures, you're walking over and over and over again. The most expensive walk in our current representation with the triangular substitutions is when the variable isn't bound, because then you have to walk all the way to the end of the substitution. Of course, that's not counting the case where you have this triangular structure, right, where you have to follow the chain and you have the n squared behavior. But I think in practice, most of the time when the lookups are expensive, it's because you're looking up a variable that's not in the substitution at all. So that's something where using a hash map or something like that would speed things up quite a bit. Okay, well, that's pretty much all I have for today. I think we can, now we've talked about unification and substitutions and all that, we should do the conjunction, disjunction, and kind of putting all the pieces together, putting the goals together, stream manipulation, all those sorts of things next time. All right. So, any questions or comments or thoughts on any of that? Okay. Peter saying, recently released assembly-based Bones implementation seems to run MK numbers quite well. Peter, what implementation is this? Okay, yeah, if you could send a link to that. I don't think I've heard of this. Yeah, I'd like to see this. Is this basically a new compiler? Is this like a new scheme compiler like Stalin that's really fast? Okay, call with current continuation Bones. Okay, I hadn't heard of Bones before. I'll have to look that up. Okay, so apparently it does pretty well with numbers in miniKanren. I hadn't heard of that. Oh, okay, I think I had seen this. Okay, cool. I will put in a link to the okay. Well, it's good to know that the performance is decent there with even with the Oleg numbers. All right. Any other questions or comments? There were lots of good questions about substitution representation and lookup and all that. So that's an area I think could definitely explore in much more detail, or also revisit some of the ideas like idempotent substitutions, revisit ideas like union find and other data structures and so forth. So if you're interested in that, look at the paper by Lindsay and by Dave and Lindsay, and I mean my name's on it too, and Dan's name's on it too. But they did a lot of the benchmarking and all that. So yeah, so that's a good place to start if you want to think more about different data structural representations. Or you could also look at CoreLogic and how CoreLogic does it. The other thing is if you want to make the language more generic, if you want to have support for sort of more generic programming, generic unification, then you could look at how CoreLogic does it with their protocols and things like that to try to have different unification over different notions of data structures and things like that. Another thing, of course, going back to data, going back to garbage collection, the topic of garbage collection, sort of one last thought on that. Let me do the screen sharing again. What ends up happening is, you might have a substitution where, x is bound to 5 and y is bound to 6 and all this stuff. And then over time, you end up building up, consing onto this thing, and then finally you end up with w, y, z or something like that is bound to 8 or who knows what, right? But you might have a substitution that has a million elements in it. And it may be that some of these elements, like y is 6, x is 5, maybe that some of those variables you'll never use again in the rest of the program, okay? And you might even be able to tell as a human, you might be able to tell from an analysis standpoint or even a runtime that x.5 will never be used again. In miniKanren, we're not, with this association list representation, we don't have any way of getting rid of this binding x.5. It's just there forever. So, doing garbage collection inside the substitution would be quite nice. And an example of this that's kind of annoying is that right now we don't have. Here's speaking of problems. In Prolog has an underscore symbol, which means unify against anything. Sort of like in pattern matching, match against anything. We don't really have that in miniKanren, and for reasons that I'm happy to get into. But basically, if we want to have a unify against anything, then we have the equivalent of saying unify underscore with 5. Okay. That'd be sort of the miniKanren equivalent, or maybe you have a pair of things, x underscore, maybe, and you have you're unifying against 5, 6, something like that, and for some reason you only care about the first binding. Okay, in miniKanren we don't have a way of having some special unify against anything symbol or anything like that. And it has to do with the fact that we're first class, and I can get into that another time as to why we don't have that anymore. We did it a long time ago. But one of the issues is that if you want to use this style of pattern matching, say, or unification, to say we don't care what value is associated with underscore 0, well, too bad, because what you ended up with is x.5 underscore .6, and this underscore .6 is taking up space in your substitution. And if this is a recursive goal, you could end up with your substitution full of these underscore dot somethings, right? They take up space just like any other binding. That's unfortunate. That's unfortunate. So there are a couple ways maybe around it. One would be in our pattern matching version, our matchy version, to have a special underscore that really does behave like the Prolog version of underscore. Maybe we could figure out a meaningful semantics with equal with something like an underscore that ignores that part of the structure. There may be other ways around it. Another thing would be having some sort of garbage collection inside of substitutions if we know something's not reachable. So those are all issues that would be interesting to play around with or explore. Yeah, the reason that are underscore, we don't have something like underscore in Prolog with equal is that in Scheme, because we're in Scheme, we can have things like lambda x, right? We could do something like lambda x fresh nil equal x5 equal x6, okay? Now, if I showed you this piece of code, you'd probably want to be able to say something like, well, I don't care what term x is coming in, this fresh is going to fail, right? Because it can't unify x with 5 and x with 6 at the same time. The tricky part is if you have underscore as some sort of first class object like we used to, like we actually had a special underscore object that was recognized in unification. So we could write stuff like equal underscore 5 or more likely equal x underscore 5 6, that kind of thing. So underscore itself was a first class value. Part of the problem was you could do something like pass underscore into this lambda x thing, and once you did that, then underscore would happily unify with 5 and with 6 at the same time, and you would get basically inconsistent results. You'd violate really important properties of unification. So that's why we went away from that model. So at least having a first-class notion of the special underscore thing that unifies with anything, that seemed to lead to trouble. Maybe we just weren't thinking as creatively as we should, or there should be a different way to do it. But that's why we got rid of it a long time ago. Okay. Let's see. Seems like doing garbage collection is tricky when you backtrack. Well, yeah. So once again, we don't really have a notion of backtracking. We just forget stuff, right? Because it's all persistent. So yeah, the garbage collecting, with an A list, it's I think annoying because what you'd have to do, I think, is build up a new A list, and it would potentially be you potentially have to rebuild the entire association list. I don't think it'd be a problem with backtracking. You would just, upon backtracking, which kind of doesn't exist, we would just go back to the old association list. But I think the problem is rebuilding the association list over and over again is extremely expensive. So we probably need to use some other data structure that would more efficiently allow us to collect things when they aren't useful anymore. Wasn't this garbage collection related to useless substitutions? If by substitution you mean one of these association lists, those things do get collected. So entire substitutions get collected all the time. If you look at a miniKanren run, it spends a lot of its time doing garbage collection, a lot of its time. So there is tons of garbage collection going on. Otherwise, because we're not using a depth first search, we're using like a interleaving search, which is more like breadth first search in its memory usage. We would never be able to get away with that if we weren't doing very, very serious collection of the substitutions. But within a substitution, we can't ever collect a binding. That's the levels of collection I'm talking about. Let's see, can you explain a little more how the underscore is useful in modeling? A slightly more complicated example. Well, I guess, let me think here. If you think of destructuring a list, that sort of thing, maybe like if you want to write an accessor for a list, like say you're using a list representation of a term, say instead of using a record, you're using a list containing 5 elements or something like that, and it's positional representation of different parts of a data structure, and you only want to get the 5th element or the 3rd element of the list, right? Well, in logic programming, unification is how you build stuff, but it's also how you tear stuff apart. So what you want to do is take in this list, or a term. I mean, it could be a fresh variable. You want to unify that fresh variable with a list containing 5 things, but you only care about the 3rd thing in the list. In that case, you might use underscores for all the other positions. And I can make that more concrete real quick. So say for example, say we're doing a cheesy representation of I don't know, what's maybe a student record, right?
Hey, well, it's Nahal. Sorry to interrupt.
Sure.
So I think I got it, and then you can continue explaining by just chime in for a second. Is it sort of like if you have many don't cares, and so you don't want to just allocate a bunch of sort of silly variable names that don't mean anything. Is it like if there's one thing, maybe it's not a big deal to have a variable name, but if there's going to be a bunch of things that you're going to be essentially indifferent about, maybe it's cleaner. And I couldn't figure out if it was some sort of optimization aspect to it, though. I don't know if that made any sense, but this is my small comment.
Okay, so first of all, here's the example, and see if that matches your intuition. If we want only the person's major, right? Right, it'd be like if you just want the person's major, then you want something like this, right? Sort of metaphorically like this. And what you don't want to do, and so you're doing a unification, but you really only care about the third thing, right? Like you only want the computer science part to match, and you don't really care about these other parts of it, right? So you know, if you want to have a special distinguished underscore operator that you can pass around, or if you just use the symbol underscore, you know, the thing is as long if a term is also allowed to be underscored in general, you can play this. You can get into trouble of passing the underscore around in some sense and unifying the same underscore with X and Y and getting weird circumstances. But this is a sort of thing where you would want to use an underscore where you don't care about anything other than the major of the person, and you're doing lots of these unifications, right? Like you don't want to introduce these other bindings in the substitution for no reason. You know, you're going to quadruple the amount of space you take in your substitution for sort of no reason. So that's the idea. Okay, so does that give you the right? Yeah. So many don't cares. That's right. Yeah, many don't cares. That'd be equivalent to that. Exactly. Did that answer the second part of your question, or? Okay, cool. Let's see. So Daniel, since you get structural sharing from the old list, I don't know how much you'd benefit from there. Are you talking about from the garbage collection, or rebuilding the you're talking about rebuilding the association list or substitution in order to, yeah. I think you would have to use a data structure where you still got structural sharing, but where it was reasonable to delete things also. So some sort of tree structure where you're able to remove stuff as well. And another thing that might be interesting would be something like a zipper type data structure to move around the substitutions or things like that. I don't know. I mean, there might be other fun stuff you could do with some of these clever data structures. Yeah. With respect to underscore, maybe special operator like discard with a conjunction. Yeah, so I think, Daniel, are you saying that that maybe we want to like remove or kind of scope the associations in our substitution and like throw them away or something like that? Yeah, there may be something with some notion of lexical scope, and eigenvariables, which we'll talk about another time, kind of have that notion. That can get tricky and expensive to enforce in the implementation, and you just have to be careful you don't break any of the semantics. But yeah, that would be another possible way to do it. So that'd be interesting to think about. I mean, so that's a pretty straightforward, in some sense, problem. Is how do we get something like these don't care or unify against anything but not end up with problems like, the thing we want to avoid is this sort of thing, right? Because, if I were doing some sort of static analysis, let's say, right, or just as a human reasoning about this code, as soon as I see these two unifications, I know they can't possibly succeed, right? So I could even throw that code away. And as soon as you have underscore, that violates that reasoning, unless you handle it very carefully. So some sort of underscore that we could use with equal equal would be cool. The other possibility is we could use match-e, which looks much more like Prolog style syntax. With match-e, you have some expression you're matching against, like we could match against this thing, some data coming in, and we have different clauses, and the first thing in the clause is like a pattern, and in this case, the pattern could be like this, and here the don't care states. Here the don't care sort of symbols, they're not really first class, right? I mean, you can't reuse the same underscore. So we could do it within match-e because we have special syntax. We're not allowed to pass these underscores around. They really are syntax. That's an obvious way to do it. And I think our current version of match-e, the version I've been using, I'm not 100% sure that the underscores really work right, or if it even has underscores. So cleaning up match-e to really handle this correctly would be one way around the problem. It would still be cool, because I tend to use equal equal, not match-e many times. It'd still be nice to have an equal equal notion that made sense. But that'd be another option, to just say, well, if you really want to do that sort of unification with don't cares, then you should use match-e, which is based on syntax, not higher order, or so you can't pass things around with lambdas and so forth. So that'd be another way around it. Okay, good questions. All right, well, I think we're about almost 2.5 hours in or whatever, so I think that's probably a good place to call it. But yeah, thanks for joining me, and Happy New Year, and next time we can do some more implementation, and then after that start getting in some papers and playing around with stuff, or just see what people come up with. I mean, we're already at the point now where enough I can share real problems, open problems. So if you want to play around with any of this stuff and do some show and tell, I'm all ears. So. Daniel's saying maybe a fresh major discard. Okay, so Daniel's got an idea. Let me just see. Sure. So going back to the kind of going back to this problem, Daniel's suggesting maybe something like this. I guess this is lexically scoped. Is that right? So would it be kind of like that kind of thing? Okay, within the body of the discard, it'd be treated as a regular variable, but it would be eliminated from the substitution before going up to fresh. So would this be like, is this one supposed to have 3 ticks or something like that? Okay, so maybe some local thing. And I guess in some sense discard is special syntax, and so it feels like you need maybe some sort of syntactic support. So maybe this would be a way of doing syntactic support. Yeah, so okay. yeah, so you could have something like that, which can be lexically scoped, and we'd have these special discard patterns. And yeah, and then I guess it just does regular unification, but then throws away the underscores outside the scope of this. So yeah, that would be a way you could do it also. Yes, you need to prevent those leaking out. So I think there are ways to do it, and they have different trade-offs that we'd have to play around with it a little bit to decide which one made most sense. But something like this discard form might be a good way to go. In some of the classic logic puzzles, like the zebra problem or things like that, you can often end up with lots of these don't care type things. And when you want to try, or like I guess the 8 queens problem is a good example. If you want to do a totally pattern matching version of 8 queens, you have lots of don't care states all over the place, that kind of thing. And it's unfortunate to be adding to the substitution all over the place. That's a little unfortunate. Yeah, okay. So Igor, you've got some logic problems to show next time. Very cool. Good. Okay, well, next time we can do more microKanren-y implementation things and look at Igor's problems. And if anyone else has played around with these things, we can look at it and slay more trolls. Yeah, so next time Daniel's a pretty good troll slayer, so I'll give you guys the what do you call it, the control room stuff. That worked pretty well. You're much faster at that than I was. Okay. I think I'll stop the broadcast, and thanks again. Happy New Year, and see you next week.